Hello students and welcome back. So now we are going to discuss more combinational circuits, and the first one among them is a multiplexer. We are going to talk about a 2x1 multiplexer design in this video. So in this video we are going to talk about that what is a multiplexer, what is the working principle of a mux. Multiplexer is in short called a mux. How to design it using data flow and gate level modeling. So let us get started. So multiplexer, before I discuss anything on the digital design side, you must have heard a term called multiplex or the movie multiplex. Well, in almost every shopping mall we have a multiplex where you have multiple screens and different movies are being screened on these. When you go there, you decide to watch one of them, not all of them at a time. And how do you decide that? You need to have some selection criteria. The criteria can be based on the language of the movie, or the main lead character in the movie, or the reviews on the internet or from your friends. Based on these combinations, you decide only one of the movies. And that is what exactly we do in the digital circuits as well. A multiplexer can select one out of n possible inputs, and that input will be assigned as the output. The selection is done using the decision making signals. So there are n inputs and we have a few selection lines as well to decide that which input will be selected. If I have only one selection line, I can make two decisions, yes or no. That means 0 or 1. If I have two select lines, then I can have four different decisions, 0 0 0 1 1 0 1 1, and that is how using n select lines we can choose from 2 raised to power n different inputs. In digital design, the multiplexers are normally termed as 2 raised to power n cross 1. So if n is equal to 1, it will be 2 cross 1. For n is equal to 2, it will be 4 cross 1 multiplexer. So let us talk about the simplest one, and that is a 2 cross 1 multiplexer. There are going to be two inputs. We are naming them I0 and I1. If there are two inputs, we need only one select line and the name is S. The output variable is Y and the values of input variable will be assigned to Y based on the value of S. If S is 0, we say Y is I0. Otherwise, Y is I1. That means if S is equal to 1, then Y is equal to I1. So this is the block diagram that we have, and here we have two inputs on the left side, select line on the bottom, and on the right side we have the output variable. When we talk about the functionality, the truth table is that we are going to have three input variables in this case. Two inputs are I1 and I0 and one input variable is S. So we have total 8 cases, and you can see in the first half of the table when S is 0, whatever is the value of I0, same is the value of Y. And in the second half, whatever is the value of I1, same is the value of Y. When we solve the truth table, we get the Boolean expression as S bar I0 plus S I1. That means when S is 0, I0 is selected, and when S is 1, I1 is selected. So if we want to implement it, we can do it using one NOT gate, two AND gates, and one OR gate. So now we are going to implement this multiplexer using data flow as well as gate level modeling on Vivado. So here I have multiplexer 2x1 using gate level. So I am taking inputs I0 and I1 and S, and then I have output Y. My expression is that Y is equal to S bar dot I0 plus S1 S dot I1, right? So that means I need to take some temporary variables called signals also. I take wire, one is S bar, then I need something to be stored which is AND of S bar and I0. I can call it P, and then I need another to have AND of S and I1. Once I have these, then I can start writing the gate level coding. So we write note, output variable is S bar and input is S. Then we take AND, output variable is P and inputs are S bar and I0. Then we have another AND which is output Q. Output is Q and inputs are I1 and S. So now once we have P and Q, then we say OR, output is Y and inputs are P and Q. So here we write the semicolons, all four AND module, that is fine, and we save it. One thing which is advisable, that you should also mention some instantiation for these gates, but that is optional, but a good practice is that you mention these. So now we save it and let us see that what will be the schematic. So we have the schematic I0 with S bar, I1 with S, and then we have the OR gate. Now let us code it using the data flow as well. So in this code, we define our Y as register. There is a small correction in the code which is shown on the screen. In line number 30, we should not mention always alone, but we should mention the sensitivity list as well. So we should write always at the rate I0 or I1 or S. And then in between the begin and end of always, we define one procedural assignment that Y is equal to not of S and with I0, here will be ampersand, that means and then or with and of S and I1. So this is the code, we save it and see that what is going to be the schematic this time. And we can see that the schematic is exactly same, S bar with I0 and S with I1, and then we have the OR gate. So in both the cases we get the similar schematic. Now very quickly we will see the simulations as well. So we can see the simulations. Whenever S is 1, for all these values, whatever is the value of I1, here it is 0, here it is 0, here it is 1, here it is 1, it is same. And when S is 0, in all these cases, whatever is the value of I0, the same is being reflected here. So students, now we know about 2x1 multiplexer. Let us design a little more complicated one, that means 4x1 mux, in our next video. Keep learning. Thank you.